So I believe now you all can see the screen and we can get started. So welcome to the probability tutorial. And as mentioned earlier, this is supposed to be a refresher tutorial and not supposed to be something where I teach you probability from scratch, right? So this is supposed to be things that you are already supposed to know. So this is for machine learning and reinforcement learning. So let's get started. So in this tutorial, we are going to cover pretty much everything that is needed for the machine learning and the reinforcement learning course. And so if you go through it properly, then you should not have any trouble after the tutorial in any of those courses, right? So we'll cover all the basics and base rule, conditional probability, random variables, independence, and expectations, variance, and multiple random variables. And if we have some more time left, then we will also cover some of the important distribution functions, which are it's good to know, but if you don't know it, then you can always look it up online, right? So okay, so let's start with the basics. So I'm not really going to spend a lot of time in basic because it's really very basic. So first, let's get settled on the notations, right? So we will use omega for the set of all basically our sample space, which is set of all possible outcomes. We will denote events with some capital letters, not necessarily E, which is going to be a subset of set of all possible outcomes, and the probability will denote it with the capital B and the event in the bracket. Okay, so the properties. These are very basic properties. So probabilities are, as you all know, that it's between 0 and 1. It's basically number of favorable outcomes divided by total number of outcomes, which is why it's between 0 and 1, right? So the probability of the entire sample space is always 1. If A is a subset of B, there are two events, A and B. If A is a subset of B, then probability of A is always going to be less than or equal to probability of B. Right? All of these are very intuitive. This one is seems a bit heavy, but it's not that heavy. Probability of A and B happening together is obviously going to be less than any one of them happening on its own, right? So and finally the union one, which is A or B, both of them, or one of them, at least one of them happening, it's less than or equal to probability of A plus probability of B, because they sometimes will have some intersection in it, right? So this becomes an inequality. So this will become an equality if we have what we would call exclusive events, mutually exclusive events, right? In this case, what we have is intersection probabilities are 0. Any of two of them happening together is always going to be 0. Right? It's not possible, basically, and that's why this union inequality will become an equality here. That's the same equation, just more complex form of writing the same equation. Okay. So now let's jump onto something more important, which is conditional probability and the base rule, right? So let's say we have an event, which is, let's just call it event A, and we have another event, let's call it event B. And let's say we are interested in finding out what is the probability of A given that event B is always happening, right? So in other words, this event B, the green circle, will become our total set of outcomes, or the sample space. And this intersection section, right, this will become our favorable outcomes, because that's when A is also happening out of all possible cases where B is happening, right? So we are basically trying to calculate this area, the intersection area, divided by the total area of the B. So it's exactly the same thing. Probability of A given B is probability of A intersection B divided by probability of B, right? And similarly, I can also calculate probability of B given A, which is this intersection divided by this red circle probability, right? So using these two equations, what we can do is we can actually find out the probability of A intersection B by just pushing this denominator to the other side. Okay, and this is this is the kind of equations we'll get from both of them, right? So for this one, we'll get the probability of A given B times probability of B. That's same as probability of A intersection B, and the similar thing from the other equation. And what we would like to do is, like, if we are asked to find the probability of A given B, then what we'll do is we'll use this equation, right? And what we'll do is we are going to substitute this one over here, right? So this way, like, we'll have probability of A given B in terms of probability of B given A, probability of A, and probability of B. So because like a lot of times it is kind of hard to find this A intersection B probability. So we just substitute all these numbers into it and it becomes slightly easier. Okay, so that's what we can call as the base rule. It's exactly what I just told you, like we just substituted one part in the numerator, and that's where we have the base rule. Okay, so this is so far very simple, but what we can do is, like, we can even make it even more complex, and just because like we like complex things, we can see that probability of B can be seen as, B can be also seen in two different ways. Like, so one is like we can just directly put probability of B, but if it is not that easy to calculate probability of B, then sometimes what we do is we divide B into also a bunch of events which are happening at the same time. So in this case, let's say we can say that probability of B is same as probability B happening while A is happening and B happening when A is not happening, right? So that's basically this stuff. So this is same as like probability. First, we basically measure B in terms of A, where we say that probably A is happening, and given A, B is also happening. And the other part is that A is not happening, and given A is not happening, B is still happening, right? So this becomes my total set of outcomes. And one of my favorable outcomes, this one part is basically my favorable outcome, right? So we just substitute this probability of B in the denominator, and that's where we get the complex form of the base rule, right? So it's not really very complex. It's just like, if you try to remember it this way, then it sometimes becomes trouble, but otherwise it's kind of very easy to understand. So that's base rule. And now let's talk about independence. So by the way, if you have any question at any point of time, feel free to like just raise your hand and I'm going to unmute you. Okay, so let me see if there are any questions. Okay, I don't see any questions as of now, so we'll keep going. Actually, I don't even see the Zoom screen. Do I see the Zoom screen? Am I even sharing the right screen? Can you all see? Can somebody in the chat point it out? Yeah, okay, sounds good. Okay, I can see the chat also, so it should be fine. Like, yeah, if you have any questions, just put the question in the chat. I can see the chats. All right, so let's get back to it. Independence. So we'll say that even two events A and B are independent if and only if we have the probability of intersection of those two events is exactly same as multiplication of this individual probabilities, right? So that's when we will call that those two probabilities are independent. So now what will happen to the base rule if we use the independence part, right? So if two events are independent, then what will be the probability of A given B, or rather B given A? So if you recall, this was the formula earlier where we had A intersection B on the top. And if we substitute this part, where A intersection B is basically A times B, then B will cancel out and we will be left with probability of A. So basically, in other words, what we are saying is that probability of A given B is same as probability of E. It doesn't matter whether B is happening or not, because A is independent from B. All right, so that's the basic thing that you need to remember from independence, right? So one is that this part where the probability of how do you decide whether two events are independent or not, like just try to compute this part. And if this is always satisfied, then those two events are independent. And the second part is that the conditional probabilities are same as like the other event is absolutely not even needed, right? So it's not even in the picture. Okay. So now let's jump on to some more complex stuff, which is random variables. So random variables are basically functions. Okay, so they are not really variables. They are called variables, but they are basically functions. So they map events to a real number, right? So every event they'll say that this event is mapped to certain real number, and these real numbers don't really need to follow any range or anything, right? So it can be any number between -infinity to +infinity. Unlike probabilities need to be between 0 and 1. So for example, let's say we are tossing 2 coins, right? In that case, our event space will be this kind of things where we have 2 heads and tails, tail and hand, and 2 tails. And one example of random variable can be, I want to count the number of heads for every possible outcome, right? So this is a function, and it is mapping all of these events to a number between 0 and 2, right? So that's my random variable. So we can calculate even the probability of a random variable or the function taking a particular value like this. So assuming that the coins were like kind of fair and those 2 tossings were independent, in that case, we get this probability of 1/4 because that's the only event where we have 2 heads. Okay, so this was an example of a discrete random variable where my function range is kind of discrete, like it's the function can only take these 3 numbers as the out. It can only output these 3 numbers, but the random variable can also output a very continuous set of real numbers, right? So in that case, it can be a continuous random variable. Okay, so that's the random variables, and now we'll talk about more stuff about random variables. So it's basically, we'll start with the discrete random variables. And for the discrete random variables, what we have is something called probability mass function. So we'll denote it with the small p, and if it is not clear, then we will also put this x at in the subscript, just to make it clear that we are talking about this mass functions of this particular random variable. So it will map the range of that function to some probability, which is between 0 and 1, right? So what exactly it is, it's basically we are a particular number, small x, which is a real number, right? So what I'm trying to say is that this random variable taking the value x and its probability is given by this p function, probability mass function. Okay. This is for the discrete random variables. And yeah, so at this point of time, I want to ask, like, can anyone tell me what will happen if I, let's say, try to sum it up for all possible values that these random variables can take? And if I try to calculate the probability of that random variable x. So, okay, we have some questions. Random variables could be a mix of discrete and continuous function too. I don't really understand that question. So it would basically like your sample space. If it is continuous, then most likely your function is also going to be a continuous random variable. Otherwise, it's going to be a discrete random variable. I'm not sure how it will be a mix of discrete and continuous random function. But anyways, can somebody answer me what is the value of what I have written on the slides? Okay, so that is 1. So people are watching this, they are not asleep. So good. We can carry on. So of course, as we saw, like the probability of entire sample space is 1. So this the entire sum. If we sum it over all possible outcomes, then it is going to be 1. Okay. Moving on. Now we'll jump on to continuous random variables, where we have something similar to probability mass functions. It's called the probability density functions, right? So we'll denote it with this small f, and it is somewhat telling me the probability of that particular random variable taking a particular value, but it is not exactly telling me that thing. So what it tells me is that my random variable taking a value between a range, which is small x and small x plus delta x, right? So it doesn't give me a probability of a particular point, because when we have continuous random variables, probability of random variable taking that particular single point value is always going to be 0. So what we measure is the random variable taking values within certain range, and that is given by this probability density function. So it is probability divided by the range. Okay, when this range is very small, then it is approximately equal to the value of that function. So Andrea is saying that I speak about the mix of direct distributions and continuous functions, for example. Okay, I still don't understand. Let's take this offline sometime, like after the tutorial, because let's carry on with the tutorial. But the idea is that sometimes you'll be dealing with discrete random variables, sometimes you'll be dealing with continuous random variables. I'm not sure if any point of time you'll need to deal with something sort of a mixture, right? So we'll revisit that later if it is needed. Okay. So, okay. Moving on. Now we'll talk about expectations and variance. So this is something that we'll be using a lot in the course, machine learning course, and even in the reinforcement learning course. So expectation. So what is expectation? So first of all, we'll be measuring expectations of a function. Okay. So for a function g, how we will measure the expectation is that we'll go through all possible values of that random variable. So expectations are always with respect to some random variable, right? So we'll denote it if it is not clear in the subscript. And what we'll do is we'll just go over all those possible values and see what is the value that g function takes and what is the probability of random variable x taking that particular value, right? So this is the way you calculate the expectations. If it is a discrete random variable, if it is a continuous random variable, all you have to do is just replace this sum by an integral, and voila. So basically you integrate from -infinity to +infinity, and you put the probability density function instead of probability mass function, right? So that's how you calculate the expectations. So let's start with this example, right? So we have an expectation of, so earlier we saw that the random variables themselves are functions, right? So we can also always calculate the expectations of a random variable, which is e of x, and this is how it is calculated. So random variable will take the value x, and we just multiply it with its probability of doing it, right? So this is again for the discrete one. The continuous one, you just integrate it. Okay, so can anyone tell me what is the expectation of a constant? Okay, I see a bunch of zeros. Some of them are saying the constant itself. Okay, so all you have to do is basically just put this constant function in this formula, right? So what you will get is, so the people who said 0, you need to you're wrong, because let's see why you are wrong. And people who say it's constant itself, you are right. So let's see. Okay. So the expectation of a constant, what we do is just put this constant in place of x, and a constant is going to always take the same constant value, and we can always take it out of the summation. And what we are left with is this part. And one of you already, in just a couple of slides ago, told me that this value is 1. Right? So what we are left with is the C. So expectation of a constant is the constant itself, right? So always, if you ever get confused, just remember this formula. This is about how you calculate the expectations. If you are clear about that, then you will not make mistakes. Okay. The more important rule that we'll be using in both the courses, it's called linearity of expectations. So what it says is basically, if you have to calculate expectations of a bunch of functions which are added together, then what you can do is you can basically calculate the expectations of all of them individually and then add them up together. So if you have a linear combination of functions and you want to take the expectations, first you take the expectations of individual units and then do the linear combination. So it is allowed. with expectations. All right, so we'll be heavily using this in both the courses. So make sure that you are comfortable using this kind of rule for expectations. Okay. So let's actually see an example in variance, right? So what is variance? Variance is basically the measure of spread around its mean. So how like sometimes like all the variables are going to take very close values which are very, very close to its mean, and sometimes they are kind of very spread around its mean. So variance is kind of something that is going to give us more information about that, right? So what I'm going to measure is that I'll see what the random variable is taking the value, and I'll see how far it is from the expected value. I'll take the square of it, and I'll take the expectation of this entire complex thing in the brackets, right? So that is my variance. And this is obviously very like complex way to calculate variance. So what we're going to do is we are going to simplify it, right? So we'll first expand this square, and it will be like this. So now we have three parts. This is 1, this is 2, and this is 3. And we'll basically take the expectations of all of them using linearity of expectations, right? So what I want is basically expectation of x square, first term, second term is expectation of this term, and the third term is expectation of this term. So all the time we are taking expectation with respect to the random variable x. And when we take the expectation with respect to random variable x, this e of x term is a constant here, right? So x is something that is going to change, but the expected value of x is a constant. So we can always take it out of the expectation. And so as we saw earlier, like the expectation in this case, like the last term, expectation of this is a constant, right? So this is a constant. So expectation of this constant is going to be itself, right? So let's see how things go. We take this expectation of this constant is itself, and we take e of x outside of this expectation, and what we are left with is e of x times e of x, which is e of x squared. And when we simplify all these things, what we are left with is expectation of x squared minus expectation of x to square, right? So this is like very easy way to calculate variance if you are asked to do so. So using this, can somebody tell me what is the variance of a constant? Okay, I see a bunch of people replying. This time, all of you are getting it correct. It is 0 because this is all you have to do is just put that constant instead of x, you just put that constant here, and it will become c square minus c square, and it is 0, right? So yeah, good job. Now let's take about what is the variance of constant times a random variable x. So we already know that the expectation of cx is basically c times expectation of x, but I don't know about this one. So can anyone tell me? Okay, so we have one answer. Can we have more answers? Is that correct answer? So again, like all you have to do is just put cx here and try to simplify it and find out the answer. COV is bilinear. We are not really into covariance right now, but okay. So yeah, yes, you guys are getting it correct. So good job. So moving on. So we have what we just saw is that variance of a constant is 0, and the variance of c times x is c squared times. So I'm hoping that like the slides were kind of uploaded a day before. So I'm just hoping that you are not like just looking into slides and giving me answers, right? So just calculate all this stuff, and you should be actually comfortable with calculating this kind of things. Okay. So now let's jump on to something like make things more interesting by adding more than one random variables. So what we'll get is, so earlier we have a distribution function, probability distribution functions. When we have more than one random variables, you can write variance with covariance. It's a way to show variance. Yeah, we'll come to covariance in some time. So yes, that's you're correct, Andrea. So okay, so we have so when we have more than one random variables, so will usually be given a joint distribution function, right? So it is basically saying that if we have these n random variables in our thing that we are dealing with, in that case, we'll be given with this kind of a joint distribution function, which is kind of saying that what is the probability of x1 taking this value small x1, x2 taking this small x2 value, and so on and so forth. So not exactly those particular point, but like you know what the probability distribution function represent, right? So that's what will be given. And sometimes we want to find a marginal distribution function, which is to say what is the probability. I don't care about all these other variables x2 to xn. I only care about x1, and I want to find a distribution function for x1. So what is some function which tells me that what is the probability of this x1 variable taking a bunch of values which are function of which are basically some x values, right? So how do we calculate that? It's this way. So it's not very complicated. All we have to do is just basically integrate with respect to everything else, right? So leave x1 there and integrate this joint probability distribution function with respect to x2, x3 up to xn. If you do this, then what you end up getting is a function of x1, and that is your marginal density function. Okay, so I hope like this is clear to you. If you ever need to calculate the marginal density function given the joint distribution function, joint density function, then this is how you calculate it, right? So is there any confusion in this? Because this is something that we'll be using in the course, and I think there are some questions in your assignment 0 related to this also. Okay, so let's take it even further and let's try to measure the conditional probability when we have more than one random variables, right? So what we are trying to measure is what is the probability of x1 taking value x1, given that x2 to xn have already taken this value up to x2 to xn, right? So it's again very simple. So we'll again do the same thing. Like we'll just say that our total outcomes are these things where x2 to xn are taking these values x2 up to xn. So note that there is no x1 here. So how do we calculate this? Can anyone tell me how do I calculate the denominator? How do I find out the denominator given that I have the joint PDF? Yeah, exactly. That's correct. Integrate the x1. So if you just do the exact same thing that we did earlier. So here we wanted to find x1. So we integrated with respect to everything else. And here on the other side, we wanted to find everything else. So we want to integrate with respect to x1. Right. So when we do that, we get the total outcomes, and our favorable outcomes is given by this joint distribution functions directly. Right. So it is like x1 is taking value x1 and x2 to xn are already taking those values. Right. So this is how you calculate the conditional probability. Now let's, like for two variables, it is kind of sometimes more useful. So we want to calculate probability of x given y. In that case, we have this joint function, probability of xy, and in the denominator, we'll have probability of y taking the value y. So y can take the value y in, like again, we just did exactly the same thing that we did in the base rule. We break it down into parts where x is taking a bunch of values, right? So x is taking different values, some different x prime values. And given that x is taking those x prime values, we calculate probability of y given x is taking x prime value, right? So that's my total outcomes, and this is my favorable outcome, right? So it is exactly the same thing as this thing, where I just say that x is taking x and y is taking y, given that x is taking x. So this is a form of what a rule that is called the chain rule that we'll see, right? So it's kind of very easy to understand. We first fix the value x, and then we try to calculate the value of y with respect to x is taking value x, right? So in more general, you can do it even with more than two variables. It is like this way, like we first calculate the probability of first variable taking that value, then the second variable taking the second value, given that the first one has taken the first value, and so on and so forth, right? So this is the chain rule. And what happens if all those random variables x1 up to xn are independent? So in that case, what will happen is all these conditional probabilities, right, will become like the individual marginal distribution functions, because like this probability of x2 given x1 is same as probability of x2, because x2 is not dependent on x1, and so on and so forth, right? So what we'll get is, if we this probability, which is in this case it's a joint distribution function, will be like the multiplications of each marginal distribution functions, right? So if you have to ever find out whether a set of random variables are independent or not, all you can do is just take a look at its joint distribution functions and try to find out its marginal distribution functions and see if this equation is holding or not, right? So if this is holding, then you can say that it is those variables are independent. Okay. So for independent random variables, we have one more property for expectations. So we have x and y, there are two random variables which are independent, and we have two functions, g, which only depends on x, h, which only depends on y. Then we can, if we have to find out the expectations of multiplication of those two things, then we can just split it into two parts, where first we take the expectations of g, and second we take the expectations of h, and then we multiply them together, right? So that's another way of doing things when we have the variables which are independent, right? So this is an important property, just remember that. Okay, so now we come to what is called the covariance, right? So we saw how we calculate the expectations, right? So if we have to calculate an expectations of a function which depends on two random variables, then we basically sum it over all possible values of those two random variables and multiply them with their joint joint probabilities, right? So that's how you calculate expectations. When you have continuous random variables, then you, instead of summing, you just do the integration and you get the same thing. And the covariance is basically, this is how you calculate it, right? So it is basically, you take the random variable x and see how far it is from the expectation, and you take the random variable y and you see how far it is from its expectation, and you multiply them together. So it is in a way variance, but it's more like covariance. It's like how my x is spread with respect to y, okay? And like the y is spread with respect to x and everything. Like so that's how you define the covariance. And if you simplify this term, you will get something similar that we saw in the variance calculation. It is expectation of xy minus expectation of x, expectation of y. Okay, so here is the question. What happens to these expectations when we have x and y are independent? So what is the covariance of x and y? Somebody in the chat can answer. Yeah, okay. So that's exactly correct. So that is 0, because in that case, you can just split this expectation, because expectation of x, y is same as, expectation of x times expectation of y. Okay. Okay, you are asking some question, x minus e of x, y minus e of y. Yeah, that is correct. That's what I have written in the slides. Is there any mistake in the slide? Yeah, I think, yeah, what you have written is correct. So these are not two individual expectations. I think you are supposed to club them together. Okay. So I think I'll correct this slide. So this is basically what they're saying is that this formula is probably wrong. It's supposed to be expectation of this first term, x minus ex, times this second term, which is y minus ey. and then you calculate the expectation of this entire thing. Yeah, so that's the correction. So this is the correct formula. Okay, let me actually take the screenshot. This is the wrong formula. Okay, so I'm going to take a screenshot of this so that we don't lose that. Okay, carry on. Let's carry on. So if X and Y are independent, then the covariance is 0 because they are not dependent on each other. So that's another way of saying that. Okay. When we have more than two variables, what we will be dealing with is called covariance matrix. Is basically you just put all this x1, x2 up to xn on the rows, on the top row, and on the columns, and then you calculate the individual covariance for each terms, right? So x1, 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 x2 up to xn, x1, xn, and so on and so forth, right? So this entire matrix is called the covariance matrix. And if you put all your random variables, x is basically like the column vector of x1, x2, xn. So here what we have is we have our x is basically x1, x2, and so on. Right. In that case, you can write it even in this formula, right? So it is expectation of x minus ex, x minus efx transpose, and then you multiply it, and then you take the expectation, right? So it's exactly the same as what we saw in the previous slide, except there was a mistake in that slide. So this is like the correct formula. Okay, so that's the covariance matrix. And for the covariance matrix, we have some important properties. So it is always positive semi-definite, and it is always symmetric. So as of now, we'll not talk much about this, but these are kind of useful properties. So you should, every time you deal with covariance matrix, so just remember that those metrics are always positive semi-definite and symmetric, right? So, and I think this is like the last topic that we'll be talking about. It's called the law of large numbers. Okay, so let's say that I have a random variable and it is following this kind of distribution function. And let's just say that this is the mean. Let's denote the mean by mu, right? So this is my random variable x. Now, if I want to calculate the mean of this random variable by experiments, then what I'll do is I'll basically take independent samples and try to calculate what is the mean by taking the mean of those independent samples, right? So that's a very, very common way of calculating the mean. But in that way, if I calculate it that way, then I might not get the same mean as the original mean. I might get, let's just say, something over here, right? So this is, let's just call it, I take n independent samples and I take the mean of that. So what I end up getting is something like this. So I basically make this kind of an error in measurement, right? So this, let's just call it epsilon. So basically, law of large numbers says that this error, right, it becomes smaller and smaller as I take more and more samples, right? So more and more, if n is very, very large, then this error will reduce, or rather the probability of making the same error will reduce, right? So that's basically the law of large number. Let's see it in the theory. So we basically take n samples of that random variables. We can also call them like individual random variables because they are basically independent from each other and they're kind of also a function of x. And we measure those values, and then we take the mean of them, and let's just call it x n bar. And that's what we are trying to approximate. Now, the expected value of this x n bar is exactly same as the mean, but it is not always going to take the value mean of that mean, right? And variance of this is going to be whatever was the variance of my original random variable, right? So it was, original one was x with, let's just call it, it has mu as the mean and sigma as the standard deviation. In that case, my variance was sigma square. And if my variance of x was sigma square, then this variance of x in bar will be given by sigma square by n. Right. So again, like this is like the standard calculations that you can do even using the formulas that we saw earlier. Okay. So the law of before we see the law of large number, we have something called Chebyshev's inequality, which is kind of saying basically the same thing, right? So we have this random variable. This is mu, and here it was our x in bar, and this is my error, right? So what it is saying is that the probability of me making an error, which is larger than epsilon, me making an error of larger than epsilon, is exactly equal to this sigma square by n times epsilon square, right? So sigma square comes from my variance, and that's going to stay fixed. If my error is reducing, right, then this probability will go up and up very high. And if my n is increasing, then also this probability is going to be decreasing. Okay, so if epsilon is increasing, then probability increases. If epsilon decreases, then this, okay, I messed it up, but basically you got the point, right? So epsilon square is in the denominator and n is also in the denominator. So if you take large number of trials, then this probability basically reduces. And what you end up getting is like, in other way, it's like you are less likely to make the same error, or you'll be making smaller and smaller errors as you increase the number of trials. Okay, so that's the law of large numbers, basically. So the law of large numbers is saying that if I take infinite number of trials, then I'll exactly get the same mean that I was expecting. Now, I think we are mostly done with the tutorial, so I'm just going to go through some of the probability distributions and see if you, like these are basically important distribution functions that you'll be seeing frequently in the course, right? So first one is the uniform distribution function, which is like probability of every outcome is exactly the same. And this is how you define it. And its mean is basically, it's the middle point, basically the range, the a plus b by 2, where like if your random variable is going to take the values between a and b. This is how you can calculate the variance. So you can actually even like, do this kind of stuff. And it's like as an exercise, you can try to derive these formulas for mean and variance. Mean is basically expectation of x, and variance is what you saw, like expectation of x square minus expectation of x square. Okay. So that's uniform distribution function. And then we have something called Bernoulli distribution function. That's also something that we'll be using quite frequently. So here, my random variable is going to take, it's a discrete kind of random variable. It's only going to take the values 0 and 1, right? And 1 is called the success, 0 is called the failure. The probability of success is given as p. Probability of failure is 1 minus p. And if I take one trial, then what will be the probability of what will be the distribution function is basically, if I get the, if I get the success, then I get it, I have P. If I get a failure, then I have Q, right? So at one point of time, any one of them is active, the other one is deactivated. So you can actually even write it in this form. If you don't like exponentials, then you can write it as a linear combination of this, x times P times plus Q times 1 minus x. So this is so far so good. And if you try to calculate the mean using expectations and everything, then you get the mean as P and the variance will be PQ, right? So again, like it's a good exercise if you want to calculate all those things. And now let's take something which is more general than this, which is called binomial distribution. So previously we were just taking one trial, and now we are going to take n trials. So for each trial, I have the probability of success as P. I don't care about the probability of failure at this point of time. So out of n independent trials, I want to calculate how many successes I'll get. So if I want to find out the probability of getting X successes, and I can still choose out of n which x I'll get the successes. And those x will have the probability of p, and the other n minus x trials will be failure, and it has the probability of 1 minus p. Right. So if you put n equal to 1, then you jump back to the Bernoulli distribution. Right. So you get the mean as np, variance as np times 1 minus p, which is, you can also 1 minus p, you can write it as q if you want. And the last one is the Gaussian distribution. So this is kind of the most common one, which we end up using a lot. So you don't really have any choice other than memorizing this formula, right? So the distribution function is given by this kind of things, where sigma is your sigma square is your variance, and sigma is your standard deviation. So this is how you calculate it if you have one variable, and if you have n variables, more than one variables, then this is how you calculate it. Right. So here the capital sigma is your covariance matrix. Right. So we saw earlier how to calculate the covariance matrix, and its mean and variance are given here. So that brings us to the end of this tutorial. And if you have more questions, we can talk about them. So we have like too much time left. Any questions? So I'll wait for a couple of minutes for you to like come to the questions part. If you don't have any questions, you can leave the meeting. Okay, thank you for attending. So I hope this was useful, and it should help you with your assignment 0 also. And yeah, we'll see you guys again in the other tutorials. Is the tutorial going to be available on Moodle? I think so, yeah. So this tutorial is recorded, so it will be also posted in YouTube. So that's the YouTube channel, and you can actually even see the recording from there. You already have the slides on the course website, which is Sarath's website. And I think the video link will also be there in the Sarath's website. So I'm not sure if it will be there on Moodle or not, but it is obviously going to be there on the website. Okay. So you'll see the link in the Sarath's website for the YouTube video. Okay, so I'm going to stop the sharing, and I'm going to stop the recording.